What we talked about last time was basic elementary reaction steps that allow us to do chemical reactions. Often we stitch multiple of these kinds of steps together, but if you have this toolbox of steps in your mind, then you can understand mechanisms which are just individual steps strung together. For example, classic one is addition to a carbonyl carbon to give you a tetrahedral intermediate. Nucleophile lone pairs, which are the HOMO, attack the LUMO, which is the pi star, at the carbonyl carbon, break the pi bond, get this tetrahedral intermediate. Another elementary step is elimination, where a lone pair on an atom adjacent to a leaving group kicks down and the leaving group leaves. That's the elimination step. Of course, nucleophilic addition step is going to be favored by carbonyl compounds that are very electron poor, like level 1. Elimination is going to be favored by really good leaving groups, and we've talked about what those are. Another thing that you should be prepared to see a lot in different forms is proton transfer, or acid-base chemistry, or deprotonation and protonation. This is where a base, lone pairs on a base, attack the hydrogen to whatever it's bonded to, sigma star, breaking that bond, and the base makes a new bond to the hydrogen. You end up with the conjugate acid of the base here, and the conjugate base of your acid. This happens a lot for a lot of reasons, but one of the most important reasons it happens in biological reactions is to make something that's a good nucleophile. So I illustrated that here with this example of a ketone, which is not a great nucleophile, but if a base removes the proton that's alpha to the carbonyl carbon, the corresponding conjugate base is stabilized by resonance, and you can use that conjugate base, which is called as an enolate, you can use it as a nucleophile. So sometimes you'll see reactions where your starting material is water and you want hydroxide to attack something. Well, first you got to make hydroxide. You're just going to use a base to do that, often a group from an enzyme active site. Another example of acid-base chemistry is if you have a tetrahedral intermediate where you don't have a good leaving group, the negatively charged oxygen can pick up a proton from an acid to become this sort of addition product. So we'll see proton transfer all the time. One thing to remember about proton transfer is it's generally fast and easy. And so it can be a very reasonable step to take in various reactions. Finally, I showed you one that those three are going to be the main ones: addition, elimination, and proton transfer. One that you won't see a ton, but it tends to be important for organic chemists, so that's why I'm showing it to you here, is a direct substitution reaction where the nucleophile attacks the carbon leaving group sigma star. You get a new nucleophile carbon sigma bond and the leaving group leaves. Most of our chemistry is going to focus on the first three of these reactions, and we'll see only a few examples of the fourth one. All right, so that's your toolbox. We went through a couple of examples last time. The first one, nope, that's the exam key. Wait a minute, there we go. The first one was hydrate formation, where you have an aldehyde and you end up adding hydroxide to the carbonyl carbon and you add a hydrogen to the carbonyl oxygen. The way that proceeds is hydroxide attacks the carbonyl carbon, breaks the pi bond. Where do you get hydroxide from? Well, you've got to deprotonate water, so likely another molecule of water deprotonates the purple one so that it can attack. And then lastly, where do you get the proton for the carbonyl oxygen? Well, you likely need to steal it from this water molecule. And we said that you can do all of this, a deprotonation, an attack of a pi star, and a protonation, and another deprotonation, all in the same step like this, or alternatively, if you prefer, you can go stepwise. You can have water deprotonate another water molecule to make hydroxide, then hydroxide attacks, pi bond breaks, Then you protonate the tetrahedral intermediate on the carbonyl oxygen using the hydronium that you made in this previous step, and that gives you the hydrate product. Both of those mechanisms are okay. They're both fine, and it's fine to draw them either way you want. This one takes a little bit less time, so that's often what I will do. The example or illustration of that kind of mechanism came in your quiz 12, where we started with this aldehyde, which happens to be a carbohydrate. And in the product, you can see that the alcohol oxygen has formed a bond with the carbonyl carbon. And what used to be the carbonyl is now an OH group. So you can tell that this involved addition of a nucleophile to the carbonyl carbon. And you'll need to get good at looking at starting materials versus products to get an idea of what happened here. The presence of the new bond here between oxygen, purple oxygen, and blue carbonyl carbon is evidence of an addition step. So how are you going to get the alcohol to attack? Well, you need to deprotonate it first. So we remove the proton from the alcohol. It becomes the negatively charged alkoxide. Then the lone pair on that negatively charged alcohol attacks the carbonyl carbon. Then the pi bond breaks. And then where do we get the proton to put on the pink oxygen? We get it from this water molecule. And so through this sort of series of arrows, we can have water do the deprotonating and the reprotonating all in the same step. That gets you to this product, which happens to be called a hemiacetal. More on that later. We'll say what that word specifically means. But what used to be the carbonyl carbon is bonded to an OR group and an OH group. And this happens all the time. This molecule here is actually glucose. And this is the cyclic form of glucose. And this is the major form that glucose exists in. One of the reasons it exists there is because you've got a level 1 electrophile in the same molecule as a potential nucleophile. So the reaction happens very quickly. An alternative way to show all of this in a stepwise way would have been first deprotonate the alcohol, the purple alcohol, to make the alkoxide. Then the alkoxide attacks the pi star, breaking the pi bond. Then you protonate the negatively charged oxygen on the tetrahedral intermediate, and that gives you this hemiacetal. The trick, what's on the left looks very simple what's on the right looks very simple compared to what's on the left. The trick is I've abbreviated everything I possibly can in the drawing on the right. For example, this R group here is all of this stuff that the aldehyde carbonyl carbon is bonded to. And this R prime group here is all of the stuff starting here and going back around that the purple alcohol is bonded to. And in reality, the R and the R prime or R dash or R apostrophe groups are linked together. That doesn't matter for our abbreviation. You're welcome to abbreviate molecules as I've done here, and that will tend to simplify things in terms of the mechanism. One of the skills that you want to develop is the ability to zoom in on the parts of the molecule that matter and temporarily forget about the parts of the molecule that don't. Questions about that? That's an example of a deprotonation, an addition, and then a reprotonation. All right. Let's keep going with that mechanism handout. Nope, not that one. There we go. Nope, also not that one. That's the one. Okay. The next one on our mechanism is another example of several addition and proton transfer steps together. I should put a plus sign maybe between the two. Addition plus proton transfer, and there's even an elimination step. So we're going to use these three in our toolbox. This example comes from what I told you about how you see. We actually learned about this. This molecule is 11-cis-retinal. We looked at that when we were talking about cis and trans alkenes and learning to assign E versus Z. This is the key pi bond, the cis pi bond, that isomerizes or switches to trans when this molecule absorbs light. Light promotes an electron from HOMO to LUMO. That weakens this pi bond, allows you to rotate around it, and that causes a change to the protein that houses this molecule. And that protein senses the change and then engages in a series of downstream signaling reactions that ultimately turn into a nerve impulse that your brain interprets as sight. Okay? So this is the 11-cis-retinal molecule. Before it can absorb light and transmit that signal, it has to be covalently attached to the protein. And we're going to show you how that happens. So you have a level 1 aldehyde here, carbonyl carbon and carbonyl oxygen. That's how I would start if you're looking at something and you don't know what to do. Look for a level 1 electrophile. And then look at the next step and see if you can tell what has happened. I've got on this aldehyde, my leaving group, my Y group is a hydrogen. And I can see that that hydrogen is still there in the next step. Here is what used to be the carbonyl carbon. And here is what used to be the carbonyl oxygen. And now it's got a hydrogen on it. This R group, I assume, I'm going to highlight it in gray, must be the rest of the retinal molecule, which we're just abbreviating as R. The other thing you notice, a couple of things have changed. You see a nitrogen bound to the carbonyl carbon. That's a clue that the nitrogen is the nucleophile. The aldehyde is a level 1 electrophile. And then also shown over here is an HA. What do you think that's for? Go ahead. Right, you want to, in the product, you have what used to be the carbonyl oxygen, you have a hydrogen. That's got to come from somewhere. And indeed, if we protonate the aldehyde, that's going to make the carbonyl carbon even more reactive. So if you were going to draw a mechanism for this first step, where should I draw I'm going to have the nucleophile attack the electrophile. I should start my arrow with lone pairs on the nitrogen. Where should that arrow point to? Carbonyl carbon, good. And then what? Am I done? What do you do when you dump electrons into a pi star? You always break the pi bond. Good. So electrons will go out onto the oxygen. And then lone pairs on the oxygen will deprotonate whatever this acid is. This is likely some acidic group in an enzyme active site. You've seen examples of what those could be. That could be a carboxylic acid as an example. Okay, does that get us where we need to be? That accounts for the new bond between carbon and nitrogen. That accounts for the sigma bond between carbon and oxygen, and it accounts for the OH bond here and the presence of the conjugate base there. So that was what we just did there, was a combination of addition and proton transfer. If you wanted to show that stepwise and redraw the structure, you certainly could. Go ahead.
So I want to know why it would continue reacting the oxygen goes with the hydrogen, because it could just sit, it has 4 bonds at that point. Why does it?
So you're asking, why don't we stop here and not do this?
Yeah.
Let me draw the intermediate that would form. And that's the question. That oxygen would, you're right, the carbonyl carbon would have 4 bonds to it. The oxygen would be negatively charged. And the question we ask when we get to a tetrahedral intermediate is really, do we have a good leaving group? And the answer here is the hydrogen is certainly not a good leaving group. This protonated nitrogen could leave as a neutral nitrogen. And that's actually a reasonable backward step. In fact, that can happen. There are some mechanistic steps that are in equilibrium. They can go forward and then they can turn right back around and go backwards. So what you're sort of suggesting is a possibility. However, the reaction conditions in the enzyme that, the reaction conditions promote this kind of thing happening, in part because the product is more stable than the starting materials. I'm not sure that answers the question, other than if you look at what's going to happen next in this reaction, it makes sense why we would need to protonate this oxygen. Let me just give you the big 30,000 foot view. In the final product, the retinal is going to be covalently attached to what used to be the nitrogen. You're going to have a weird functional group here that's called an imine. You haven't seen imines before, but this is like the nitrogen version of a carbonyl. Notice the oxygen is gone. We got to get rid of the oxygen somehow in this reaction. And the way we're going to do that is by protonating it. If the oxygen's negatively charged, it's never, ever, ever going to leave. So we're going to use proton transfer to turn it into a good leaving group. Follow-up question?
So is it just more to get more in a stable condition? Because I understand like why the double bonds would need to make it
Yes.
lone pair. It's just for stability.
Right. With that, so you're totally okay here. You're just like, why do I need to protonate that? And the answer is doing so allows you to access a more stable product ultimately. I would not have expected you to predict that what's going to happen here happened. But the real question is, if I tell you what happens, can you come up with reasonable arrows? And that's generally how I test mechanism questions. I'll show you a starting material and an intermediate, or a starting material and a product, and I'll say which arrows are reasonable. You saw that on one of the exam questions. There was a bunch of potential mechanisms for reactions, and you had to judge which one made the most sense. And that tends to be how I ask these questions. So I wouldn't have expected you to guess, oh, you could have definitely guessed nucleophile attacks carbonyl carbon. I wouldn't necessarily have expected you to guess, and that oxygen has to be protonated. But if I told you that it was, could you draw the arrows that get it there? All right, other questions? All right, so looking at that intermediate that we got to, we have what used to be the carbonyl oxygen, we have an OH group, and then we have this positively charged nitrogen. Now, if you look at where we're going to end up, we want the nitrogen to stay, and we want the water to leave. And right now, the nitrogen is a decent leaving group. It's positively charged. It could leave as a neutral amine. And if you look at the next step, where we are next, you can see that the nitrogen is no longer positively charged. Again, the reason nature's doing this, the reason nature's going to remove a proton from that nitrogen is so that that nitrogen can stay around more. So if I wanted to remove a proton from the positively charged nitrogen, what's the best way to do that? Got a negatively charged conjugate base, so how do I draw the deprotonation? Lone pairs attack the nitrogen-hydrogen sigma star and the bond breaks. that restores our acid that we started with, and it gives us this neutral intermediate where the nitrogen is no longer a good leaving group. Okay? So one lesson here, as we're learning from this, is that nature uses proton transfer to stop things from being good leaving groups when it wants those things to stick around. And you're going to see in the next step that nature uses proton transfer to turn previously bad leaving groups into better leaving groups when it wants to get rid of those things. As I said, since our target is to get to this imine where 11-cis-retinal is linked to a protein in your eyes, we got to get rid of the oxygen. OH minus is not the best leaving group. So what nature's going to do, if you compare to where we're going, look and see that OH minus has become ROH2 plus. How did that happen? We took lone pairs on the oxygen, we attacked the hydrogen, and we broke the hydrogen bond to the bond to whatever in the acid the hydrogen was bonded to. That converts just the neutral OH into this OH2 plus group, which is now a great leaving group. You can tell that it's a great leaving group because it would leave as neutral water. Neutral water's conjugate acid has a pKa of -2. And so that's on our list of extremely good leaving groups. And if you look at what happens in the next step, water is gone from what used to be the carbonyl carbon, and in its place, we've got a new nitrogen carbon pi bond. So starting with this intermediate, how do I get rid of the hydrogen leaving group? What do you think happens? Got any ideas? What kind of reaction would do that? Yeah, in an elimination reaction, recall you've seen a prototype elimination reaction before. The players are going to be different here, but the overall trend is going to be the same. An atom with lone pairs that's adjacent to a good leaving group can kick electrons down and kick off the leaving group. Right? So we've said water's the good leaving group, and there is an adjacent atom with lone pairs. So to do something similar, where should I draw my arrow? Start it with the lone pair on the nitrogen, then what? Gonna make a pi bond that attacks those electrons are attacking the carbon-oxygen sigma star and breaking the carbon-oxygen sigma bond. And that creates this new functional group where a nitrogen is pi bonded to the adjacent carbon. And then to get to the neutral imine, we just need another proton transfer reaction. We're gonna use the conjugate base of our acid that we made before to deprotonate the positively charged nitrogen, and that gets us to this imine. Now that's probably the hardest mechanism we've done so far. And as I said, you're not expected to predict what the product would be. You've never seen an imine before at all. The point here though is, or maybe you did only for a moment when we talked about vision. The point is, if you're given the steps to get from start to finish, if you're given all the intermediates, can you push the arrows in a reasonable way using addition, elimination, or proton transfer? Notice how that first step was an addition step, these two arrows, and proton transfer, these two arrows. Notice how the next step is what kind of reaction? Talking about here to here. What kind of our addition, elimination, or proton transfer? Yeah, proton transfer. Proton transfer is going to be attacking of a proton by a base. Addition will be attacking of a carbon by a nucleophile. How about this next step? What kind of step is that? Look at what's being attacked. Okay, some of you were saying addition, some of you were saying elimination. And both of you are wrong. Focus on what's changing. In an addition reaction, your nucleophile attacks a carbon. In an elimination reaction, adjacent lone pairs kick off a leaving group in the same molecule. In a proton transfer reaction, lone pairs on a nucleophile or base attack a hydrogen or a proton. We'll use those terms, hydrogen and proton, interchangeably, because a hydrogen nucleus just has one proton in it. So, with that in mind, what kind of step is this? Yep. Proton transfer. We already said this was an elimination. Lone pair kicks off an adjacent leaving group. How about the final step? What kind of reaction is that? That's also proton transfer. Okay. That's pretty difficult, but even the most difficult mechanisms that we will do are addition reactions, elimination reactions, and proton transfer reactions. So my goal for you is to look at something like this and see the pattern. All right, I don't have another example of imine formation on your quiz because this is maybe one of the hardest mechanisms we'll do today, and I didn't want to overdo it. But it might be worth you going back and trying to work through this on your own when we're not sitting together and see whether you can talk to yourself about what each kind of step is and how to do it. Are there questions about that as you look at it? Anything you want to know? Anything that doesn't make sense? Don't feel pressure to nod your head and move along. Slow us down and force us to stop and talk about it. Or we can sit here staring at each other. That might be nice too. No? Yes, thank you.
We have hydrogen as the leaving group and water leaves. Can you just walk me through that a little bit? Maybe I'm
You mean this step?
Yes.
Okay. So here, if you look at what used to be our carbonyl carbon, it's still bonded to the R group, still bonded to the hydrogen, now bonded to the nitrogen because that's what happened earlier. And now we took what used to be the carbonyl oxygen, we previously turned it into an OH group, and then we added a second proton so that now it's OH2+. It can leave as neutral water. And the question is that a good leaving group? The answer is, well, look at its conjugate acid, which is hydronium and has a pKa of -2. So this OH2 with a positive charge on the oxygen is a good leaving group. So we know that good leaving groups can leave, especially if they have adjacent kicker-offer atoms. We've never seen a nitrogen do that before. Most of the time when we do an elimination, right, it's been the oxygen kicking off the Y group. Here, and maybe I should have changed the coloring for this purpose, maybe I should have said, hey, the hydrogen's not a great leaving group, now the water is a good leaving group. And so on an adjacent atom you have lone pairs, they can kick down and kick off the leaving group in the same way that a negatively charged oxygen can kick off a leaving group. That's the pattern. So it doesn't have to be oxygen and it doesn't have to be negatively charged, but you do need a lone pair adjacent to a leaving group.
Okay, that makes more sense.
Good. What else? Yeah. What does the squiggly line mean? Good, thank you. That means there's something large over here that I didn't want to draw. So the squiggly line means other stuff over here, where that other stuff is the entire opsin protein that has thousands of atoms in it. Yeah.
Isn't that the R group?
No, the R group is this, tens of atoms that are the retinal. So the opsin protein is over here attached to the nitrogen. Any place there's a squiggly line, we could write opsin. So this reaction loads a large molecule, 11 cis retinal, onto another even larger molecule, the opsin protein. And when they're together, it makes the rhodopsin. Okay, what else? All right, we're going to do several examples of this one. So let's work on this next example of the mechanism handout, and then we'll go to the quiz. I think, yeah, why not? So this reaction is called saponification, which is the soap-making reaction. You use hydroxide that you get from lye, and then you use triglycerides. Now, for simplicity's sake, I've just got a monoglyceride here. This used to be a triglyceride, and it's already gone through a couple other reactions first. Doing this just to be simple. Notice the long nonpolar tail. Notice the ester carbonyl carbon. Notice the ester carbonyl oxygen, and then notice this OR leaving group. And we don't need to worry about all of it, just sort of this portion. That functional group is an ester. What level is an ester on our list of electrophiles? That's 2. So better than an amide, but not as good as an aldehyde or a thioester. Now, let's look at the next step and see if we can detect what has happened. Find what used to be the carbonyl carbon. It's right here. Find the OR leaving group. Find what used to be the carbonyl oxygen. And then find what else has changed. What do you notice there? What else is bonded to the carbonyl carbon? Yeah, that OH. Where do you think that came from? Of the starting materials that you have present, where do you think this OH came from? Is it obvious, so nobody wants to say, or it's confusing? I think, are you worried about whether it's this one? No, or this one? Okay, it should be hydroxide. This one is negatively charged. This OH group is bonded to an adjacent carbon. It is not negatively charged. So it's negatively charged things are more reactive than corresponding neutral things. So if you were going to homo-lumo this one, where am I going to draw my arrows? To the carbonyl carbon and break the pi bond. Are you seeing a theme? That's going to show up in a lot of these. Okay? Does that explain the new bonds? Yeah, it explains the new bond between carbon and the OH group. It also explains why the carbonyl oxygen is negatively charged. Okay? Now, if we keep going, in the next step, what we see is the OR group has left. And what we're left with is our carbonyl oxygen, our carbonyl carbon, and then the OH group. So, what kind of reaction mechanism is this step right here? Elimination. You can tell because an adjacent lone pair on the carbonyl oxygen kicked down and the leaving group left. All right. Good. And that first step was an addition step. Notice that when you do addition plus elimination, the net effect of that is the reaction we call nucleophilic acyl substitution. The acyl group is the blue carbon and the pink oxygen. We call it a substitution reaction because we substituted out the green thing and substituted in the purple thing via addition and elimination. Now, interestingly, what is this functional group that we just made? Yeah, it's not an alcohol because it's got an adjacent carbonyl. This is a carboxylic acid. And the pKa of that carboxylic acid, if you looked it up, would be around 4. And in the product, you can see that we no longer have the carboxylic acid, we have the carboxylate. And we no longer have this green alkoxide. Instead, we have an alcohol. Let's ask the question, is that reaction reasonable? Well, first, let's ask the question, what kind of reaction is this? We go from carboxylate and carboxylic acid and alkoxide to negatively charged carboxylate and neutral alcohol. What kind of reaction is that? Yep. Proton transfer. Good. H plus means proton. The proton that gets transferred is this one. Now, how could you tell if that was reasonable or not? What's the pKa of an alcohol? Right? So in an acid-base reaction, the strongest acid loses its proton and the weakest acid doesn't. So actually, it's very reasonable for this negatively charged alkoxide to deprotonate the carboxylic acid, and that gets us our product, the fatty acid carboxylate and the glycerol. And this then is how you make soap. All right, nucleophilic acyl substitution, proton transfer as needed. So now with that background, you're now prepared to look at sort of the reverse of this reaction. And the reverse of this reaction is, what if nature, instead of making soap, because soap is what humans do when you take animal fat and you add lye, but what if your body had a fatty acid carboxylate and it wanted to make a triglyceride for storage? Okay? So we're going to do in quiz 13, there's two examples under question 1 that we want to do. We're going to start, this one's, actually I want you to start with the second one, and we'll do that one because it's a little simpler. And then, so do the fatty acyl-CoA thioester to monoglyceride. And take a few minutes, see what's happening here. I want you to identify the key electrophile in the first step and what level it is. I want you to identify the product and compare its level to the starting material and tell me whether it's uphill or downhill. And then I want you to look at each of the intermediates and see how you get from one starting material to one intermediate using some combination of addition, elimination, and proton transfer, using your intuition of homo attacking lumo. All right, so go ahead and get started on that. Take a few minutes. I'll wander around for questions. Mention that to everybody. I think there's something that got lost in a copy and paste. There should be still hanging around here the conjugate acid of your base, which you're going to need to do the final step. Good question. Others? we should do some simulated exam conditions, like I should be heckling you or trying to distract you while you were trying to solve this problem. So at first I thought about, should I be the rock section, like when somebody's trying to do a free throw, but then I can't pull that off. But I could be your future kids. So keep working while I say things like, I have to go to the bathroom, and Billy hit me, and I just threw up, and I'm hungry, and all of that stuff. All right, are you ready to talk through it? You think I'm joking about that, but occasionally, I hope when you look at your future children, you don't see my face. But sometimes weird things like that occur. For example, my youngest son, if you look at pictures of him as a kid and you compare them to pictures of my dad as a kid, it's like, whoa, spitting image, even though he doesn't look a thing like my dad now. And Amber said to me, you don't realize when you get married that someday you're going to give birth to your father-in-law, but there it is. It's our child. Weird, bizarre. Okay. Yes?
Just to make sure, we would tell whether or not something's good living group is based off of whether the acid is strong.
Based on, yeah, you can tell if something's a good leaving group based on, is the conjugate acid of the leaving group a decent acid? And the cutoff is sort of a pKa of 16. If some conjugate acid has a pKa of 16 or less, we're going to say, okay, probably a decent leaving group that a negatively charged oxygen could kick off. Okay, well, anybody want to take a chance? Yes, come on down, thank you. I will stand silently instead of heckling you, okay?
Okay.
All right, good. How do you know that you needed to deprotonate that OH on glycerol?
Well, I saw that the two glycerol and the fatty acid eventually ended up connected to each other. So I knew that there was going to be some kind of addition reaction going on, but I knew that that O needed to become negative first. Oh,
Okay, yeah, if you scroll over here, you notice that the proton is gone.
Right.
One thing I would just say at this point, you don't need the little negative that you drew on the glycerol oxygen.
Oh, okay.
Just because if you were going to draw, you were correct that if we drew this stepwise and did the proton transfer first, you are correct that the intermediate would be an alkoxide. We're drawing it all at the same time, so you don't need to do that.
Okay.
Yeah. Okay, good. Questions about that first step? Any comments? You identified that glycerol was the nucleophile because you looked over at the tetrahedral intermediate, compared it to the thioester, said what changed? Well, here's the glycerol molecule, so that must be the nucleophile. Okay, yeah, keep going.
Okay. And then over here.
All right, good. And how did you know that you needed to do an elimination reaction?
Because I noticed that the COAS negative, that one split off, so I knew it had to be elimination.
Okay. If you look at what left, do you think that's that? CoA means coenzyme A. That's a big long file, and I think we talked about last time. We'll see it again. But does that strike you as a decent leaving group, and how? How do you know?
I would say yes, but I don't know how to explain why.
So you don't need to have these numbers memorized, but the thing that left is this coenzyme A thiolate, the negatively charged sulfur. its conjugate acid, the thiol, has a pKa of 8, and that's why thioesters are good electrophiles. Okay, good. And then the last thing you need to do is what?
Last thing would be right here.
Okay, great. Thank you, very good. So in mechanisms, small things can matter a lot. So if you look at your answer and there are differences between what you wrote and what's up here, any minor details that you're noticing that you want to ask about? Any alternatives that you tried that you want to know? Is that okay too? Go ahead.
Is it important when we're like drawing pairs and stuff to draw the lone pairs, like for example on this one?
Yeah. Is it important to draw the lone pairs? My preference is to draw the lone pairs. I know when I learned, the teacher that taught me, my old Jedi master, Dr. Savage, who's still, he's here. He's not old actually, he's in his 50s, but anyway, he and I are actually PhD brothers. We were trained by the same other Jedi master, so whatever. But no, he often will show the arrow with the negative charge kicking down. I think in my mind it's technically a little bit more correct to show it starting with the lone pairs. My preference is if you're going to show a heteroatom attacking something, it's best to show the lone pairs, but that's not something that would make it right or wrong. Yeah. What else? All right. Good. Yeah, it's a good time to take a break. Let's take 5 minutes and we'll keep practicing.